we are looking at the chemistry of group 1 and group 2 elements. Group 1 being the alkali metals and group 2 being the alkaline earth metals. Having looked at the periodic properties, that is, properties that are changing within the periodic table across the periods and down the group, and among the different elements, looking at the ionization energies, electron affinity, electropositivities, and so on. Electronegativity, looking at the sorbate of ionic salts, and after that, we are able to look at the diagonal relationship. Now, we are taking our discussion about inorganic chemistry to the chemistry of group 1 elements and group 2 elements. We are going to tackle group 1 elements, and we are going to begin with physical properties of group 1 elements. The elements in group 1, you have lithium as number 1, you have sodium with atomic number 11, potassium, rubidium, and cesium. As you go down the group, of course, the atomic number increases, and almost all the outermost electrons are found in the S. And as you go down the group, also you have the changing in trend of ionization energy, the first ionization energy. It is decreasing down the group as you are coming from lithium to cesium. That is, there is a decrease in effective nuclear charge, hence the electrons can be easily be removed from the outermost quantum shell. They are not easily attracted by the nucleus as you go down the group, hence the ionization energies decrease. And as well, you expect to have an increase in atomic radius. If the electrons are not strongly attracted to the nucleus, then those electrons are very far away from the nucleus. So you expect to have an atomic radius being large as you go down the group. Also, as you go down the group, the melting point decreases. Of course, the melting point will also have to decrease because as you go down the group, the strength of the bonds that will be formed by these elements will also has to decrease. So they will be requiring a little amount of little melting point or low melting point for them to escape into that. So we have these alkali metals. Most of them are solids with a center or body centered cubic arrangement. They have one valence electron, and they have low melting and boiling points. That is, they only contribute one electron to the formation of metallic bonds. They have the largest atomic radii and low ionization energies than other elements in the period, and they are highly electropositive and most reactive metals. That is, as you go down the group, we have metallic character increasing. That is, electropositivity is increasing as you go down the group from the first element to the last element known as cesium. So cesium is most reactive than lithium, and that is why some of the times, or sometimes, you find that the lithium is possessing some of the properties resembling those of group 2 elements, that is occupying a diagonal position. You look at diagonal relationship, the characteristics or the properties where lithium is resembling magnesium. So the highly electropositive and most reactive metals, those are the elements of group 1. When you look at the elements of group 2, their physical properties, you have their ionic radius increasing also down the group. The reasons are the same. As you go down the group, there is an addition or there is an added shell. And as the shells are being added, then we are increasing the screening effect or the shielding effect beyond the nuclear charge. Hence, the electrons or the effective nuclear charge is less, and these guys are less attracted to the nucleus. Hence, they have high ionic radius. Likewise, to remove the first electron, it is a bit, the first ionization energy is a bit higher for group 2 elements, but the trend is the same. As you go down to the group, ionization energy decreases. These guys are also electropositive. For them, they are having 2 valence electrons. That is, they contribute 2 electrons in the formation of metallic bonds. And they have a smaller atomic radii than the corresponding group 1 members. Another property they have is that when you are comparing them with group 2, or when you are comparing these group 2 elements with group 1 elements, they also possess higher melting and boiling points because of the ability to contribute 2 electrons to the formation or to the electron cloud in the formation of metallic bonds. They have higher first ionization energies than corresponding elements in group 1, and they are less electropositive, less reactive, and form less ionic compounds than group 1. So as you are coming from group 1 to group 2, we are having reactivity decreasing because we are going to, a moment. We are saying these guys, they are less reactive, less electropositive, and form less ionic compounds, because as you move from group 1 to group 2, we are decreasing metallic character. We are tending to the non-metallic character of the other group of the periodic table from group 1, 2, 3, and 4, 5. The other ones are non-metals, and these ones 1, 2, 3, they are metals. So as you are tending to non-metallic character, we are reducing the electropositivity, even the reactivity is reducing, and the ability to form ionic compounds is also reducing. When we look at the chemical properties of group 1 and group 2 elements, reaction with hydrogen, you look at group 1s, they are the most electropositive metals, or the most electropositive metals of group 1 and 2. They all react with hydrogen when heated to form ionic hydrides, except for beryllium and magnesium, which form covalent hydrides. When we react to group 1 elements, that is sodium and others, you get sodium hydride, and all the others also give the same product. With calcium, it gives you calcium hydride. We call them ionic hydrides. That is the reaction with hydrogen. And the ionic hydrides that are formed, once they react with water or they are hydrolyzed to form a hydroxide, we get an alkaline solution formed once these guys react with water, and hydrogen gas is also formed in the process. Reaction with water. All group 1 elements react with water more vigorously than their corresponding group 2 counterparts to form corresponding hydroxides and hydrogen gas. And the vigor of the reaction increases down the group. So for group 1, they are more reactive to water than group 2 elements, and they form or they release a hydrogen gas from water molecule. Hence, we have a hydroxide being formed and hydrogen gas. And we are saying that the reactivity increases down the group. So as you go down the group, reactivity to water increases. This is because a group 1 element loses only 1 electron, whereas a group 2 element loses only 2 electrons. Therefore, you will require less energy to remove 1 electron than the 2 from the outermost shell. And as such, you expect group 1 elements to react faster with water than their neighboring metals of group 2. So for group 2, because you will have to first remove the 2 electrons to be replaced with a molecule from water, you will require high amount of energy. Whereas these ones that require less amount of energy, you expect them to have a very fast reaction than these ones of group 2. As the atomic radius increases down the group, you expect the ionization energy to decrease, hence increasing reactivity in each group. As ionization energy decreases, that is the amount of energy required to remove an electron. As it is decreasing, that means there will be ease with which an electron can be easily removed from the outermost quantum shell. So what does it tell us? It tells us that the lower the ionization energy, the lower the activation energy for the reaction, and the faster the reaction to take place. What is activation energy? It is the amount of energy that needs to be overcome. These elements need to overcome a particular amount of energy for the reaction to take place. So once there is a low activation energy, or once these elements need, or there is less amount of energy that needs to be overcome for the reaction to take place, that means that the reaction occurs vigorously. That is what it gives us for both group 1 elements. That is the reaction with water. It gives us an alkali and hydrogen gas. With beryllium, it does not react with water, and magnesium reacts with steam for magnesium oxide, a white salt, and hydrogen gas. As we said, the reaction is decreasing down the group, and group 2 elements react lower than, or they are less reactive to water than group 1 elements. So a group 2 element, beryllium, does not react with water, even if you boil the water or at room temperatures. But for magnesium, once you boil, that means you are turning water into steam. That is at hot temperatures or at high temperatures, we get magnesium oxide, which is a white salt, and we produce hydrogen gas alongside. But the rest of the group 2 elements, that is calcium, strontium, barium, they react with increasing vigor with cold water, forming corresponding hydroxides and hydrogen gas. Those are the rest of group 2 elements. So beryllium does not react with water. Magnesium reacts with steam to form an oxide, which is a white salt, and then hydrogen gas. Whereas these ones, as we said, reactivity increases down the group. So the vigor with which these guys react with cold water increases down the group. That means calcium, strontium, and barium, they are reacting with cold water to form corresponding hydroxides and hydrogen gas. The solubility of these guys, group 2 hydroxides in water, we find out that the solubility is high for barium. That is, it increases down the group, and it is low on top of the group. So this is because down the group, we are looking at the solubility of barium hydroxide being 3.32, and the solubility of beryllium hydroxide being 0.0. That means beryllium does not dissolve in water. Solubility per 100 grams of water at 25 degrees Celsius. So as you go down, you are increasing the solubility of these hydroxides. This is because the radius of the cations increases while the charge on them remains the same. So the charge is the same, whereas the radius is increasing. It will lead to a decrease in both lattice energy and hydration energies. This is because the charge density is also reducing. Where you get the charge, you divide by the radius. But remember, the charge is the same and the radius is increasing. So the charge density decreases down the what? The group. So there is a decrease in both lattice energy and hydration energies. But the decrease in lattice energy of the hydroxides is more rapid than the decrease in hydration energy. So as a result, we are suppressing the lattice energy, or it can easily be superseded by hydration energy, thus facilitating solubility of the hydroxides. Because the decrease in lattice energy is more rapid than the decrease in hydration energy, we have the hydration energy superseding the lattice energy. And remember, hydration energy is always negative, and lattice energy is always positive. These guys have to first separate into their corresponding gaseous ions for them to be soluble. So the attraction of water is high. That is hydration energy. Hence, it facilitates the solubility of this hydroxide in water. Another chemical property, we have reaction with acids. We have dilute and concentrated hydrochloric acids. And we are looking at group 2 metals reacting with hydrochloric acid, forming a corresponding salt and hydrogen gas. You have M salt reacting with hydrogen ions that are coming from the acid to give us M2 plus aqueous. Those are the ions, or that is the metal ion, the metal cation, and hydrogen gas is being released in the process. M can be beryllium, magnesium, calcium, strontium, or barium. With dilute sulfuric acid, beryllium reacts with hot dilute sulfuric acid to form a salt and hydrogen gas, and magnesium reacts with cold dilute to form a salt and hydrogen gas. So the conditions are a bit different. For beryllium, it is hot. That means you must increase the temperature. There is a high amount of activation energy it must overcome for the reaction to take place. For magnesium, it reacts with cold dilute to form a salt and hydrogen gas, and strontium, barium, and calcium react to form a sparing irresoluble salt, which renders the reaction passive. With concentrated sulfuric acid, the same way beryllium reacts with dilute sulfuric acid is the same way. However, for the other members of the group, they react to form a salt, sulfur dioxide gas, and water. The other side, they were producing hydrogen gas and a sparing irresoluble salt for strontium, calcium, and magnesium and beryllium, and barium, as the other ones were producing a salt and hydrogen. But here we have a salt, sulfur dioxide gas, and water for all the other elements except beryllium. With dilute nitric or with nitric acid, we are finding out that beryllium does not react with nitric acid at all conditions, but magnesium reacts with dilute nitric acid to form magnesium nitrate and hydrogen gas. We're having a salt of a nitrate being formed and hydrogen gas, and with concentrated nitric acid, the reaction is the same with concentrated sulfuric acid. Only the difference is that with nitric acid, we found magnesium nitrate, nitrogen dioxide gas, and water, whereas the other side we are producing magnesium sulfate, sulfur dioxide gas, and water. These other ones, they also react with nitric acid, we are looking at these other elements. They also form a salt, nitrogen dioxide gas, and water with a reaction with concentrated nitric acid. Reactions with oxygen. The S-block elements react with oxygen to form 3 types of oxides. We have the normal oxides, the peroxides, and superoxides. You are looking at the charge on the oxide, the peroxide, and the superoxide. And all group 1 metals form the normal oxide with oxygen. As shown below, M can be lithium, sodium, potassium, rubidium, and cesium. Whereas the elements from sodium to cesium, In addition, they form peroxides. All form normal oxides. But as you are coming from sodium to cesium, in addition, you form peroxides, as shown below. And from potassium to cesium, in addition to the ones that are formed on top, that is the normal oxides and peroxides, we form what we call the super oxides. So that means it is only potassium, rubidium, and cesium that form super oxides. But lithium is not capable of forming other higher oxides due to the fact that it is very small. The lithium ion is very small with high charge density and high polarizing power. Thus, the larger oxides cannot be accommodated around it, otherwise the compound would be highly covalent and unstable. That is why lithium does not form higher oxides. It's very small with high charge density and high polarizing power. Thus, we are having larger oxides not being accommodated around it, otherwise the compound would be highly covalent and unstable. We have all the group 2 metals. When seated in air, they form the normal oxides. And the more electropositive metals form peroxides. The more electropositive, they are the ones at the bottom of the group, the two elements at the base of group 2. That is strontium and barium. They go beyond formation of a normal oxide and they give us peroxides, as shown below in the equation. That is strontium and barium. And we are saying that the tendency to form peroxides increases down the group. It is because as the radii of the cation increase down the group, their charge densities and polarizing powers decrease. And once the charge densities and polarizing power decrease, we mean all what happens is that the larger peroxide can easily be accommodated around the cation with least polarizing, forming stable lattice, or with least polarization. So it means that if the charge density was high and there was high polarizing power, then this peroxide that is formed, because the peroxide is larger than a normal oxide, it wouldn't be easily accommodated around the cation, hence it would form unstable lattice. But when you look at beryllium oxide, is amphotolic and it shows both basic and acidic properties. We looked at it under diagonal relationship. You can look at its amphotolic properties. That means it reacts with both acids and alkalis. And as it reacts with an alkali, in presence of water, you form beryllium tetrahydroxy or beryllium tetrahydroxide. That is a complex. And with acids, it forms a salt of the corresponding acid and hydrogen gas. The other oxides, they are ionic and basic in nature. They are not amphotolic. They are ionic and basic. That means they only react with acids. They do not react with alkalis. Reactions with halogens. You look at all the metals of group 1 and 2 combining directly under heat to form chlorides. All metals, they form chlorides. An example, you have lithium reacting with chlorine to form lithium chloride and magnesium reacting with chlorine to form magnesium dichloride. You have compounds of group 1 and group 2. The compounds of group 2, of course, will be less ionic than the corresponding group 1 elements because the cations of group 2 have a smaller ionic radius than the corresponding group 1 elements. Also, the group 2 cations are doubly charged, while those of group 1 are singly charged. Therefore, expect group 2 cations to have higher charge density and more polarizing power than the corresponding group 1 cations. As a result, group 2 are less ionic than corresponding group 1 compounds. E.g., magnesium chloride is less ionic than sodium chloride because the cations of group 2 have smaller ionic radius than the cations of group 1 elements. Hence, the group 2 elements have higher charge densities and more polarizing power than the group 1 elements. The solubility of an ionic salt is determined by two energy terms, as we saw, that is lattice energy and hydration energy. We looked at that in the previous video. That is lattice energy and hydration energy. You go on and calculate these examples. You also look at the enthalpy of solution from these two different energy changes, that is combination of lattice energy and hydration energy, which gives us a Born-Haber cycle down. Factors that are affecting lattice energy, they are there. Ionic radius and ionic charge, we talked about them. Then we have some of the salts of group 2 elements. They are less soluble in water than the corresponding group 1 salts. It's because of the same reasons. The other ones have a small ionic radius and they are doubly charged than the ones of group 1. So therefore, the lattice energy of group 2 salts is much higher than those ones of group 1 elements. So the higher the lattice energy, the salts makes them less soluble. If they have a high lattice energy, that means it is tending to supersede the hydration energy. So these ones that possess a low high lattice energy, the lattice energy is superseded by the hydration energy. So you expect them to be or to attract water molecules towards themselves better than the other ones that are having a high lattice energy. You look at the sulfates of group 1 and 2. Sulfates of group 1 are white solids and are stable to heat and are readily soluble in water. That means they do not decompose on heating. But the sulfates of group 2 are white solids and sparingly soluble in water. They are less soluble in water, whereas the other ones in group 2, they are readily soluble in water. Solubility of group 2 sulfates in water, as you go down to the group, the solubility is decreasing. Group 2 sulfates, it is because the radius of the cations increases while the charge on them remains the same, which leads to a decrease in both lattice and hydration energies. Therefore, the decrease in solubilities of sulfates down the group is attributed to the fact that the hydration energy of sulfates decreases more rapidly than lattice energy down the group. But as we are looking at the solubility of the hydroxides, we found out that the hydration energy of hydroxides is reducing at a lower rate than lattice energy. So the hydration energy was superseding the lattice energy. But when you come to the sulfates of group 2, we find out that the hydration energy of sulfates decreases more rapidly than the lattice energy down the group. Hence, the solubility decreases. Solubility of the nitrates, carbonates, and chromates follow the similar trend to that of sulfates. That means they are decreasing down the group. We have carbonates of group 1 and 2 elements. The carbonates of group 1 metals, they are white solids. We say these guys are readily dissolve in water and are unaffected by heat, except lithium carbonate, which decomposes on heating. All the other carbonates of group 1, they do not decompose on heating. It is only lithium carbonate which decomposes on heating to give us lithium oxide and carbon dioxide gas. Why do we have this guy not decomposing? It is because lithium has a very small radius, giving it a high charge density and high polarizing power. As a result, it is capable of forming a stable compound with an oxide. However, as you go down the group, the radii of the cations increase, hence their charge densities decrease, and thus these guys cannot be easily accommodated around a smaller oxide due to its polarizing effect. So because this one is able to form a stable compound with an oxide ion, that is one of the reasons why it is able to release carbon dioxide, which is an oxide, and also release lithium oxide, which is an oxide of lithium, and carbon dioxide, which is an oxide of carbon. These ones of group 2, they decompose on heating to form metal oxide and carbon dioxide gases, or the carbonates of group 2. However, their stabilities increase as you go down the group. So on descending down the group, the charge densities of the metal cations progressively decrease due to an increase in cationic radius. Since an oxide is smaller than a carbonate ion, the decomposition of the metal carbonates becomes less energetically favored down the group. So as you go down, the decomposition is decreasing of these carbonates, and they are becoming more stable down the group than on top of the group, because an oxide that is going to be formed is smaller than a carbonate. Hence, the decomposition of this one becomes less energetically favorable. If the oxide that was going to be formed was large and it would accommodate all the ions, then it would be highly energetically favored down the group. You have the nitrates of group 1, except lithium. All the other nitrates decompose to give nitrites and oxygen gas. However, for lithium nitrate, for it gives a metal oxide, that is lithium oxide, nitrogen dioxide gas, and oxygen gas. All the other nitrates, they give nitrites and oxygen. But lithium nitrate gives an oxide, nitrogen dioxide gas, and oxygen gas. Reason and explanation is the same thing, why a lot of the chemistry of lithium is different from the chemistry of other elements. You look at complex formation by group 2 cations, and we say for us to form a complex, it must be favored by the presence of suitable empty orbitals on the cations. For you to form a complex, the cation must possess empty orbitals that will accommodate the lone pairs of electrons that will be donated by the ligands. So these other compounds that are going to form a complex with a metal, we call them the ligands. So the ligand comes and donates the lone pairs of electrons. And for this one to form that complex, it must have the empty orbitals. We shall look at complex formation under transition metals. So they also need to have a small cationic radius and high cationic charge. So that means elements which possess a bigger charge than the other ones, they easily form complexes than these ones which have a small charge. The tendency to form complex ions decreases down rapidly down the group with increasing cationic radius and decrease in charge density of cations. That is because the attraction for the lone pairs of electrons on the ligands decreases with decrease in cationic charge density. So if the attraction of the lone pairs of electrons is less, then you don't expect the complex to be easily formed. So as you go down the group in group 2 elements, there is a decrease in charge density and there is an increase in cationic radius. As a result, the lone pair of electrons that is going to be donated by the ligands will not easily be attracted. Hence, there is a decrease in cationic charge density. Therefore, beryllium cation forms complexes easily due to its very small ionic radius, hence high charge density. Those are the complexes it normally forms. And we looked at one of the reasons why the reactions in beryllium resemble, or the reasons why they resemble the reactions of aluminium. You look at they are possessing almost the same electronegativity, the same, almost the electropositivity is the same, and some of the reactions in which they resemble other group 2 elements. No, those reasons are why the reactions of beryllium differ from other group 2 elements. You can look at some of the reactions where these guys react to give alkalis and so on. We looked at that. Go and read about diagonal relationship and revise the previous video. You look at some of the reactions where it resembles with other group 2 elements, that is burns in air to form a normal oxide, reacts with chlorine to form, or once heated to form a chloride, and reaction with dilute hydrochloric acid liberating hydrogen gas. Elements which liberate hydrogen from its compound, they are higher than hydrogen in the reactivity series. Some of the analysis of magnesium, calcium, and barium ions in solution, when you are using sodium hydroxide solution, and you add to the solution containing an unknown cation, you add sodium hydroxide dropwise until in excess. If magnesium is present, you get a white PPT, that is a white precipitate of magnesium hydroxide insoluble in excess sodium hydroxide. And if it is calcium, you get the same observation. Also with barium, you get the same observation. A white precipitate insoluble in excess. For aqueous ammonia solution, you get with magnesium, you get a precipitate which is insoluble, but for beryllium, for barium and calcium, there is no observable change. It is because aqueous ammonia being a weak base, it does not have strong hydroxide ions in sufficient concentrations to exceed the solubility products of calcium hydroxide and barium hydroxide. That means that the solubility products of calcium hydroxide and barium hydroxide, they are extremely high, and the solubility product of aqueous ammonia being a weak base cannot easily exceed that of those ones. So that is why these guys cannot easily be soluble, or that is why it gives us no observable change. Using dilute sulfuric acid, you get no observable change with magnesium ions, but with calcium and barium, you get a white precipitate of either calcium sulfate and barium sulfate. Once you are using the potassium chromate, you get no observable change with magnesium, and with calcium and barium, you get a yellow precipitate of calcium chromate and barium chromate. But with calcium, the yellow precipitate formed is soluble in ethanoic acid. That is, if you add ethanoic acid, you will have the yellow precipitate becoming soluble. But for barium, the barium chromate becomes insoluble. When you are using ammonium oxalate, for magnesium, there is no observable change, whereas with calcium and beryllium and barium, you get calcium oxalate and barium oxalate. But for calcium, it is insoluble in ethanoic acid now, but barium is soluble in ethanoic acid. For using disodium hydrogen phosphate, this is the confirmatory test for magnesium. So as you add in little aqueous ammonia followed by ammonia chloride and then a few drops of disodium hydrogen phosphate, you get a white precipitate of magnesium, but there is no observable change for calcium and barium. Briefly, that is what we have about group 1 and group 2 elements, the chemistry of group 1 and group 2. Thank you for watching. Kindly subscribe to our YouTube channel for more videos. Thank you.